morning all of you. So let us today continue on the discussion with respect to the fully developed both hydrodynamically and thermally fully developed region. So I denote this as region 3, and we solved for the velocity profile in the hydrodynamically fully developed region. We got a parabolic velocity profile, and we also started the solution to the heat transfer problem. The first case that we took was a constant wall flux boundary condition. So q wall double prime is constant, and for this particular case we have also have shown that if your q wall is constant, that means your dt wall by dx should be equal to dtm by dx. This comes because of the fact that this is equal to h into t wall minus tm. Okay. Also we have expanded the fact for thermally fully developed flows you have the non-dimensional temperature gradient variation axially is 0. So from which we had obtained an expression for dt by dx in terms of dt wall by dx and dtm by dx, that was dt wall by dx minus t minus t wall by tm minus t wall into dt wall by dx plus t minus t wall by tm minus t wall dtm dt mean by tx. Correct. So you can note the partial and the standard derivative that I am using here. So this is a function of only x, this is a function of only x, whereas temperature is a function of both r and x. Therefore I use a partial derivative for dt by dx. Okay. So now if you substitute this result, okay, if you call this as number 2 and this is number 1, substituting the consequence 2 into 1, you cancel off these terms because they are identical, and therefore you come to the conclusion that my dt by dx should be equal to dt wall by dx, which in turn is equal to dtm by dx. And we have seen that this can be possible only if these are equal to a constant, because this is a function of both r and x, but these are only a function of x. So this can be holding true, the slopes can be the same if this is equal to a constant, and therefore if you plot the variation of temperature axially, so you can visualize for example a temperature profile so where you have t wall x here, you can calculate t mean x, and of course this is your t x comma r. So if you plot your temperature somewhere here, local temperature along the axial direction, so you can say that this follows a profile, linear profile like this, maybe somewhere at this radial location. Okay, so this is the center, and the mean profile will be slightly lower than the temperature of the at this particular radial location. So you can say that this is your, so this is at some particular radial location, we can say r equal to r1 for example. Okay, that is this particular location where I am plotting this r equal to r1, and at the wall of course that will be the highest temperature amongst all the three, and that will also vary linearly like this. Okay. So this is the characteristic of the temperature variation as far as the constant heat flux boundary condition is concerned. So all the three variations are identical, they are just parallel to each other, but they keep varying with the axial position. So that is the characteristic nature of the thermally fully developed. Of course they have to be hydrodynamically fully developed also. Now having seen this, we wanted to calculate actually the temperature profile itself. So if you substitute the fact that your dt by dx is actually a constant that is equal to some dt wall or dt wall by dx or dtm by dx into the energy equation, okay. So therefore it becomes much easier to integrate the energy equation directly. So you have u by alpha. Now the dt by dx can be replaced as some dtm by dx, now which is a constant, equal to t square t by dx square plus okay. So we have neglected the axial conduction in comparison to the magnitude of the radial conduction, so therefore we will retain only the radial conduction terms, r dt by dr. Okay. So now since the left hand side is a constant, we can just integrate it out the same way we integrated the velocity profile where your dp by dx was a constant. So this is a much simpler way of looking at the solution. So if you integrate it twice, I am not going to spend time integrating, I will give you the final expression 1 by alpha dt by dx, which is actually a constant. So I can either use dt by dx or dtm by dx, they just mean the same and they are just constants. So you have uc r square by 4 minus r power 4 by 16 r naught to the power 2 plus c1 ln of r plus c2. So this is what I get, somewhat similar to the velocity profile where you had a pressure gradient in the place of this dt by dx you had dp by dx there and you had a similar variation. Okay. So now we have to find the constants c1 and c2, and in order to do that we have to apply boundary conditions. Once again, two boundary conditions are required. Okay. So what are the two boundary conditions? Okay. So at r equal to r naught, let us say the temperature is equal to some t wall, of course, which is a function of x. Okay. So if you want to apply at a particular axial location, so that there is a particular wall temperature which is a boundary condition, and at r equal to 0 the temperature has to be finite. Now if you look at this directly, similar to the velocity profile, if for a finite temperature at the center, your C1 should directly be 0 because this term otherwise goes to infinity. Okay. So therefore we directly eliminated C1, so we can use the other boundary condition r equal to r naught, t is equal to t wall to calculate the second constant C2. So if you substitute, you can determine the constant, it will come out as so at r equal to 0, r equal to r naught, t will become t wall, this will be t wall of x minus this entire thing goes to the left hand side, this is uc by alpha into, so now this is evaluated at r naught, so this is r naught square by 4 minus r naught square by 16. Okay. So if you simplify it, it comes out as so you can take 1 r naught square into dt m by dx. Okay, I can maintain this as dt m by dx into 3 r naught square by 16. I think, can you just check if this is correct? This is t wall minus uc by alpha r naught square this R naught square cannot come here. I think this R naught square should not come here, right? So it is just 3 R naught square by 16. Okay, so this is your C2, and therefore you can substitute for C1 and C2 and write your final expression. If C1 is anyway 0, so therefore T of R comma X, so you can substitute for C2 and you see UC by alpha dTm by dx. So this is a common term here and here, so that can be just taken out as a common term. So of course you have your T wall of X, which can be written as this minus UC into we can also pull out R naught square as common by alpha. So UC, you can take out one R naught square so that everything can be expressed as non-dimensional form, and R naught square also is here, into dTm by dx, that is also common. So this will be left with 3 by 16, which is this, plus you have 1 by 16. So you have already R naught square taken out, so this will be 1 by 16 R by R naught the whole power 4. Okay, and this remaining term will be R by R naught 1 by 4. This will be minus 1 by 4 R by R naught the whole power 2. Okay, so this will be a final expression for temperature variation. Let us call this as equation number 3. So therefore you can see at this state it appeared like T is a function of only R, because your dTm by dx was constant, but once you calculated this constant C2, now it is a function of X through T wall. Therefore the final expression for T is a function of both R and X. Alright. Okay, so once you got the expression for temperature, we will go ahead and calculate the expression for the mean temperature, which we defined, or the bulk temperature or the mixing cup temperature. So how was the mean temperature defined? So we now know the variation of T with respect to both X and R. Now we should get an expression for the mean temperature varying with X, okay, and of course the wall temperature, or Tm minus T wall, okay, the difference between them. So how do we define the mean temperature? Yeah, so it is basically a mass weighted average of temperature. And how do you mass weight? 0 to R naught T into, so what is the mass? Rho into A into U. Okay, in the numerator and denominator the rho can cancel off. So you have U, and of course U is a function of only R. Okay, and what is the differential area? 2 pi RdR. 2 pi cancels in the numerator and denominator, you have RdR. In the denominator it has to be divided by the mass flow rate. Okay, so 0 to R naught, you have U of R into RdR. Okay, so therefore you have the velocity profile. I will just write down the velocity profile for you again. So your U of R is 1 by nu, okay, minus 1 by 4 nu into dP by dx R naught square into 1 minus R by R naught a whole square. So this is your velocity profile, and this is your temperature profile right here. So you have to plug both these inside, and you know, so this dTm by dx is a constant, dP by dx is a constant. Okay, So therefore you will have to integrate this with respect to r, you have to multiply all the terms with respect to r and then you have to integrate it. It is a little bit lengthy integration which I am not doing. You can also, if you find it too difficult, you can also use Mathematica and try to do the integral, but finally if you do that, the expression for Tm comes out as T wall of x minus 11 by 48 into UC r naught square by 2 alpha into dTm by dx. Okay, so this, let us call this as number 4. This is the variation of mean temperature with respect to x. Okay, so therefore you can see your Tm minus T wall is going to be a constant because dTm by dx is a constant. Okay, so the difference between the two, Tm minus T wall, has to be a constant. Alright, so once you got your Tm, now we can calculate the non-dimensional temperature. So your non-dimensional temperature is defined as T minus T wall of x by Tm of x minus T wall of x. Okay, so now you have of course T minus T wall, an expression for T minus T wall here from the temperature profile, and also an expression for Tm minus T wall here. Okay, so if you just substitute those expressions, so T minus T wall will be so you have your UC r naught square by alpha into dTm by dx into 3 by 16 plus 1 by 16 r by r naught to the power 4 minus 1 by 4 r by r naught square. So that is basically T minus Tw. There is a minus sign, but in the numerator and denominator the minus sign cancels out. Similarly Tm minus T wall will be minus of that, I cancel the minus sign. This will be 11 by 48 into UC r naught square by 2 alpha into dTm by dx. So dTm by dx cancels, your UC r naught square cancels, alpha cancels out. Okay, so this will give you an expression as 96 by 11 because you have 48 into 2, so that goes up 96 by 11 into this entire factor here, 3 by 16 plus 1 by 16 r by r naught to the power 4 minus 1 by 4 r by r naught square. So this is your final expression for theta. Now once you calculated your non-dimensional profile, now you can see the non-dimensional profile is not a function of x now. Okay, the way we defined your theta in the thermally fully developed region, theta is supposed to be independent of x, so and that is what comes out correctly. Okay, so this proves the fact that the assumption what we did, of course we use that assumption also, but that correlates with what we find finally for theta. So this is only a function of r. Now you can use this definition of theta and calculate your heat transfer coefficient. We had shown that in the case of thermally and hydrodynamically fully developed flows, the heat transfer coefficient has to be a constant. Now we have to determine what is that constant value. So for the constant heat flux case, we have arrived at the particular profile for non-dimensional temperature. So I will probably give you about 5 minutes. You can from this step calculate what is the heat transfer coefficient. I suggest all of you to do it yourself and check. Okay. So therefore finally you get your heat transfer coefficient as a constant value for a given diameter, k by d into 48 by 11. Therefore you can define a Nusselt number, okay, for internal flows based on the diameter of the duct. So it is not a local Nusselt number anymore, and if you define like that you get a constant value 4.36. So for internal laminar flows, both hydrodynamically and fully developed, and for a constant heat flux boundary condition, this is your constant value of Nusselt number 4.36. Okay. So therefore you see that internal flows are quite different. There is no local variation once you reach a completely fully developed condition, and after that the heat transfer coefficient is becoming a constant value. So even in your external flows, in one of the quiz problems I had given you a porous flat plate where your suction is continuously happening on the surface, and you are asked to prove at large values of x your boundary layer thickness is becoming a constant, and therefore as a consequence of this the heat transfer coefficient also becomes a constant. So even in external flows, if you maintain a suction boundary condition, you can show that your heat transfer coefficient can become a constant somewhere down the line. In the case of internal flows, that is true if you have a fully developed flow region. Okay, and now so this is a straightforward case, as far as relatively straightforward when you look at in terms of the simplification that we have done for the constant heat flux. Now let us look at the other boundary condition, which is your what? Constant wall temperature. So only these two boundary conditions are the primary boundary condition that we will see. One is a Dirichlet boundary condition, the other is an Neumann boundary condition. Okay. Now when you look at constant wall temperature, what this means, your dt wall by dx is 0, correct. So now let us go back to our equation for dt by dx and substitute this expression. What do you get? So if you substitute dt wall by dx is 0 in that expression, yeah, correct, this will be partial derivative, you are right. So I want all of you to also participate. You have to tell me if you apply this condition dt wall by dx is 0, what will be the resulting expression for dt by dx. Yeah, T minus T wall by Tm minus T wall into dTm by dx. Okay. So the other first two terms get cancelled off, you have only this last term. So now this is your approximation for dt by dx, right. So of course your mean temperature is only a function of x, but this T here, this is the problem, this is a function of both x and r. So now if you substitute this into the energy equation, now what happens? So you, in your energy equation on the left hand side you have your dt by dx. So if you substitute in place of that, you have now u by alpha into dt by dx. I am going to substitute this particular expression here, T minus T wall by T minus T wall into dTm by dx. So this is equal to, of course, your 1 by r d by dr into r dt dr. So now this is what you need to solve. Okay, let me call this as another equation number 1. Okay, so this is the energy equation. which you need to solve to find the temperature profile. Now the problem with this, now earlier when you had constant heat flux, the left hand side was completely a constant, okay, you had only dTm by dx, which again was a constant, therefore you could directly integrate it out. Now you have T minus Tvol by Tm minus Tvol. Now T is actually not a constant now, so this entire expression now cannot be solved analytically the way that we did last case. So therefore we have to do it numerically and also iteratively. So one way of doing it is you can guess some value of temperature profile, preferably from the earlier case, the constant heat flux case, and substitute as a first guess, and then you can integrate it along the radial direction, okay, and again get a new temperature profile and again keep putting it on the left hand side and keep doing it until you reach a converged solution, okay. So the other smarter way of doing it is again go back to our shooting technique. So we should try to reduce this equation to another simpler form where we can apply shooting technique and solve that equation. So that is what we are going to do now, okay. What I am going to do now, first let me, before going into the shooting technique, we have to prepare, we have to get appropriate expressions for dTm by dx. So to do that we will do a small energy balance. So let us look at the profiles of temperature T as a function of x. Of course your wall temperature is now a constant, okay. Now you want to know how the mean temperature is varying. Earlier wall temperature, mean temperature and temperature at any location were just straight lines with equal slopes. So now it is not the case, right. So there from the Newton's law of cooling you directly showed that the slopes have to be the same, but here it is not true. So therefore in this case the wall temperature is of course a constant, but how the local temperature, how the mean temperature vary is not clear. So to determine the variation, what we will do is just take a simple energy balance. So you take a duct, so you take a control volume, so this is your heat transfer delta Q, differential amount of heat transfer for this differential control volume, and you have some enthalpy coming in and enthalpy which is leaving. Of course there is a mass flow associated with this enthalpy, so therefore you can apply energy balance and say my del Q dot is equal to m dot Cp into dTm, okay. So that is del Q is equal to m dot into delta H dH, and dH corresponds to Cp into dTm, because this enthalpy is the mean enthalpy or bulk mean or mean enthalpy that I am talking about. So for the given heat transfer this is the corresponding change in the enthalpy of the fluid, and I can relate my differential amount of heat input to the change in the mean temperature corresponding to the change in the enthalpy. So this is the starting point of the energy balance. So I can just divide everywhere by dx. So this will be now dTm by dx will be equal to, now this is your heat transfer rate, okay. So this can be expressed in terms of heat flux. You can write this as Q double prime, which is in watt per meter square, into, if you assume that the control volume has a differential length dx, into dx into perimeter, right. So this will be your surface area where you are adding heat, alright. So this will be divided by m dot Cp, and of course you are dividing by dx. So dx cancels, and now your Q double prime you can apply Newton's law of cooling and write this as H into Tvol minus T mean, okay. Therefore you have dTm by dx is equal to P by m dot Cp, P is your perimeter, into H into Tvol minus T mean. So this is like expression coming out of the simple energy balance that you are doing. So we can, what we can now do, since your Tvol is a constant, we can write this as d by dx of T wall minus Tm, correct. T wall is a constant, so you can just introduce d by dx of T wall minus Tm. Okay, now there will be a minus sign, so we can put a minus sign on this side also, P by m dot Cp into H into T wall minus Tm is already here. Okay, so let us call T wall minus Tm as some delta T. Okay, so with this you can integrate this expression, so this will be d delta T by delta T. You can integrate this from delta T1 to delta T2. So what it means, if you have a duct, long duct at the inlet, that will be your delta T1, that is the difference between your wall temperature and the mean temperature, and at the exit somewhere, that is your delta T2. Okay, so once I have an equation for this temperature difference, T wall minus T mean, I can just simply integrate it from the inlet to the outlet, so that this should be equal to minus P by m dot Cp into H dx. So this I integrate from 0 to your entire length, or wherever, whichever location there you want to find the appropriate temperature difference. Okay, so this will give me ln of delta T2 by delta T1 equal to minus P by m dot Cp H into x. Okay, so or my T wall minus T mean at some location 2 by T wall minus T mean 1 will be equal to exponential of minus P Hx by m dot Cp. So this is my expression which tells me how the mean temperature varies, because my wall temperature is constant. If you know the mean temperature at some inlet, from that you can calculate what is the mean temperature at some location x using this expression. So if you plot this expression, okay, if you start with some mean temperature at the inlet, you will find that the mean temperature keeps varying in a logarithmic fashion like this, and it will asymptotically go and meet this T wall. When your x goes to infinity, so this becomes 0, and therefore your T mean will become T wall where your x goes to infinity. Okay, so this is the variation of your Tm, okay, the mean temperature of the fluid. Okay, now having known this, and we have this particular expression here, let us call this as expression number 4. Okay, I started with 1. Okay, let me call this as 2 now. So we will use this expression now, simplify for dTm by dx, because why we are doing this is we have a dTm by dx term in this equation, so we have to simplify this a little bit. So for that we are using the energy balance. Now we will simplify it. Also we should know how the mean temperature profile varies, so for that we can use that equation and integrate it out. So now from 2, so you can write your dTm by dx as, okay, for the case of circular duct your perimeter is 2 pi r, so pi d divided by your mass flow rate will be rho into pi by 4 d square rho av. So the velocity is mean velocity into Cp into H Tm. So H T wall minus T mean, I can replace this by your heat flux Q double prime. Okay, so this cancels, pi cancels here, d cancels, so this will give me your Q double prime will be k dt by dr at r equal to r naught. This will be divided by your rho into um into d will be r naught by 2, and I can write this as R naught by 2 into Cp. So this will be 2 R naught, yes, so that is correct. So now I can club this as K by rho Cp. K by rho Cp is alpha, so this can be written as dTm by dx is actually alpha times dt by dr at r equal to r naught divided by so this will be 2 times, so um r naught. So this is my expression for dTm by dx in terms of dt by dr at r equal to r naught. This is a little bit of mathematical manipulation, nothing more. So as far as circular duct is concerned, you are just writing in terms of your diameter and of course your mass flow rate, little bit simplification, and you get a relationship between dTm by dx and dt by dr at r equal to, this is the gradient of temperature at the wall. So this can be substituted into equation 1 for dTm by dx. So substituting into 1, so of course on the right hand side you have the same, on the left hand side you have so I am going to write my I am going to substitute my velocity profile, fully developed velocity profile for u, so that will be twice um into 1 minus r by r naught the whole square by alpha, and dTm by dx is substituted from here, so which will be, now this is T minus T wall by Tm minus T wall, dTm by dx will be 2 alpha by um r naught into dt by dr at r equal to r naught. So this is equal to the right hand side, which is 1 by r d by dr of r dt by dr. Okay, so here um cancels, alpha cancels here. Okay, so therefore your final expression which you have to solve will be 1 by r d by dr of r dt by dr, that should be equal to 4 by r naught, 2 into 2 4 divided by r naught into 1 minus r by r naught the whole square, 1 by r naught the whole square into T minus T wall by T mean minus T wall into dt by dr at r equal to r naught. Okay, so let us call this as my equation number 3. So this is the equation finally which comes to the form which I want to express as a ODE in order to apply my shooting technique. Okay, so you please stop and ask me if you have any questions, any doubts anywhere. So these are all just mathematical manipulations, I am going a little bit fast here. So now I am going to introduce a non-dimensional temperature theta or phi. I am using the phi here to represent the non-dimensional temperature. I can write it as T minus T wall by T mean minus T wall, and a non-dimensional radial coordinate r star, which is nothing but r by r naught. So this I am going to substitute into my equation number 3 and rewrite the entire equation in terms of non-dimensional variables phi and r star. Okay, so if I do that, so from this expression I get that my dt by dr is equal to Tm minus T wall into d phi by dr. So I can substitute for d by dr as Tm minus Twall into d phi by dr. Tm minus Twall cancels here, okay, and I can also define my Nusselt number as dt by dr at r equal to r naught divided by Twall minus Tm into diameter. So diameter is nothing but twice r naught. So if I use these expressions and substitute into this governing equation 3, I request all of you to do that and tell me what will be the final non-dimensional equation for phi in terms of phi and r star. So with that we will stop for today. So what do I get? So I have now, I can write this as 1 by r star d by dr star r star. Now for dt by dr I can substitute as Tm minus Twall. Tm minus Twall is a function of only x, so that can be taken outside the derivative, right. So I have Tm minus Tr into d phi by dr star. This should be equal to 4 by r naught into 1 minus, this is r by r naught is r star, so this I can write as r star square, T minus Twall by Tm minus Twall, this is phi, so this will be times phi, and dt by dr is nothing but again Tm minus Twall into d phi by dr. So this I can write as Tm minus Twall into d phi by dr at r equal to r naught. So now so I have r, this cancels here, so I have r naught into r naught square, so I have divided by r naught square here, and here I can have again r naught, and I can write this as r star. So r naught square will cancel, Tm minus Tr cancels, so therefore I am left with the final non-dimensional form d by dr star into r star d phi by dr star, which is equal to, now I have got the expression for Nusselt number as minus 2r naught into d phi by dr. So I can replace d phi by dr r by r naught as Nusselt number by 2r naught, so this will be a minus 4 into 1 minus r star square into phi into, this can be written as Nusselt number by 2r naught. So there is a factor of r naught which is somewhere I have to cancel. So this is r naught here cancels, this is r naught square, and on this side, oh okay, I think yeah, so this is anyway, I can write this as d phi by dr star, you are right. So this is already d phi by dr star, so therefore this will be in terms of Nusselt number, okay. So this is my final expression. You see this has reduced to an ODE now, I will call this as number 4. So this entire expression is now a function of phi. Now remember, phi is a function of only r. So earlier I had a partial differential equation, now I had reduced that somehow by any means of manipulation and non-dimensionalization to an ODE which is a function of r, and this is of course a higher order ODE. I can break it up into two first order ODEs and use shooting method. So we will see that in the next class, okay. I will just give a summary of the shooting method which you are already used to solve this equation, okay.